So in section 4.3, and we're looking at line 2 on the table. We're given some conditions. We have a pressure of N2O4 and a pressure of NO2. And the numbers are 0.925 and 0.151. This is all we're given, and we're supposed to fill out the rest of the row based on this. So the first thing it wants to know is Q. And if you watched the video yesterday, you already know how I'm going to calculate the Q. But if you didn't watch it, this comes from the equilibrium expression. So the equilibrium expression for this reaction, we need the products on top. So parentheses, pressure of NO2, and the coefficient is 2, so it's squared, divided by the pressure of N2O4, and the coefficient is 1, so it's just to the power of 1. I'm not going to write it down. It's pressure, so it has to have parentheses. And in fact, to make this a little more accurate, I should call this Kp. Kp equals parentheses PnO2 squared divided by parentheses Pn2O4. And to find Q, we're just plugging in our numbers that we have. So 0.151 squared on top and 0.925 on bottom. And so when I type this in my calculator, I get a long string of numbers. But this column says round to the nearest hundredth place. So it's 0.02. The next column is Q versus K. How are they related? We were given the equilibrium constant. Is Q less than, greater than, or equal to? It's on your paper here somewhere. What's our value for K? Anybody see it?
0.09.
0.09. Which means that Q is less than K. And if you're doing the number line, the arrow from Q going to K, left to right, and that tells me, without doing the calculation for free energy, that this reaction happens in the forward direction. Let's erase that. The last piece of this is to figure out the actual free energy change, and that's where this formula comes in. The delta G, or the change in free energy for the reaction, equals the standard free energy change plus RT ln Q. This term at the end is how we figure out how this works outside of those standard conditions. We have a standard delta G. It was given to us. It is positive 6.0 kilojoules per mole. Plus, and we have the gas constant in terms of joules, 8.314 joules per moles per Kelvin. Temperature is already in Kelvin. It's 298. Temperature cancels. And then my last term is the natural log of Q. Natural log of 0.02. Here's an issue. We can't just plug this in our calculator and expect an answer in the formula like this. Remember the other delta G formula where it was delta H minus T delta S? You had kilojoules minus joules. In this one, you have kilojoules plus joules. And so we have to convert joules to kilojoules because change in free energy is measured in kilojoules. So we have to make sure the units are correct. Then we can put all this in our calculator. Go ahead and type this in. I want to see if we can all get it in correctly. Quality control of the calculator and the operator. All right. So, Charlie, what'd you get?
I got negative 3.9.
Okay. So,
Or that's for the whole thing.
Yeah.
So 6.
Yeah. This was something, I did this and then I put them together. So negative 3.9. Is that what you said?
3.91.
Okay.
I messed up with negative 3.5.
So it depends on how you round your Q. Because my calculator gave me negative 3.69. The notes that I have say negative 3.2. There's some variation here. Probably all depends on how you round it. But we're all in the negative 3 to negative 4 range, right? Okay. And so when you look at this, the sign is negative. Does this agree with the other things that we said? That it will happen in the forward reaction. Is negative delta G thermodynamically favorable or thermodynamically unfavorable? And it is favorable, yes. And good. So now let's do line 5. And you can probably work this one a little faster on your own. Partial pressures, 0.736 and 0.529. Who all has all the numbers for row 5? Okay. Was that a hand up, Colin?
I don't know if I'm right. Probably.
All right, Colin, tell me your numbers. We'll check.
38.38.
Okay, good.
Q is greater than K.
Okay.
And plus 3.6.
All right.
Then that reverse.
Good. How about line 3? Who wants to give me line 3? I'm confident in our answers or don't want to speak. Do you have numbers?
Yes.
Tell me what they are.
.09.
Good.
Q equals K.
Okay.
0.
Yeah.
Nothing.
Okay, so the direction, if you look back in your notes just a little bit, when Q equals K, this is what we're going to call it. So we're at equilibrium. Yes, good job. All right, so now we've got enough of these trials to cover the rest of this page. It says using the values of Q and delta G, in trial 5, how can we tell the direction of the spontaneous direction? Okay, so what direction is this thermodynamically favorable? That's what they're trying to ask you. So we're looking at trial number 5. How do we know which direction it will be favorable in terms of Q? So we're looking at this. We're relating Q with delta G, and so since Q is greater than K, that tells us it is thermodynamically favorable in the reverse. So you can write this down. Number 5, reverse because Q is greater than K. And we also know that delta G is positive. These two things tell us the reverse reaction is thermodynamically favorable. Next one. Question says, in which trial is the system at equilibrium? I know. You already labeled it, right? Trial 3. Trial 3 at equilibrium. Now for the real question, how did we know? In terms of Q and in terms of delta G. For Q, it was equal to K. We know that's equilibrium. And delta G equals 0 for that trial. Technical difficulties here. There we go. It's at equilibrium. Q equals K, delta G equals 0. That's how we know. This one might require you to open your notes to a previous section. Have all of you look this one up. If you know what it is, don't say it out loud. In which trial is the reaction mixture at a standard state? Which one's at a standard state? So there are specific conditions for standard states. And if you look at the very top of section 4.2, the very first heading is standard states. It'll give you a list of things to look for. One of them applies to this. Is it number 7? It is, yeah. And we'll talk about it in just a second. Got a few people looking it up. Did we find it yet? Which one is a standard state? And the answer to this one, number 7, is standard state. And the reason we know this is because, here it is, Q is equal to 1. Q equal to 1 is one of our conditions for a standard state. Is this a forward reaction or reverse reaction? And we have it here. It's the reverse. And we know it's the reverse at a standard state because Q is greater than K and delta G is positive. At a standard state, this reaction is thermodynamically unfavorable. Any questions on those? So let's take a look at this graph, and the graph is already filled in for you, which is nice. And I'm going to do a really rough sketch. There. Looks just like it. It's perfect. This is part C. The plot of the free energy reaction of the mixture is plotted against the reaction quotient Q. How is standard delta G represented on this graph? So some basic labels. Here's free energy. Here's Q. So if you think back about a week, we had this term come up, state function. Remember the term? Does it click any bells? Ring any bells? There might be some bells clicking. So the thing about a state function is it doesn't matter the route that you take. Like if your drive home was a state function, it is. It doesn't matter if you take the most direct route from here to home, or if you drive to Burlington and then Flora and then to your house. It doesn't matter how you got there, you were here and now you're at home. Those are the only two things that matter, okay? So it doesn't matter that I drove all the way over here and then I drove all the way over here. The only thing that matters is we started here and we ended here. And the difference between these two is delta G. Here's the term again, a state function. Let's see, delta H is also a state function. Pretty much any of the delta whatevers in thermodynamics are state functions. All right, so next page, idea number 4, the sign of delta G tells us the magnitude of KEQ. And so we are relating standard delta G with the equilibrium constant. This is the formula on the AP sheet. This is how they relate to each other. So standard delta G is reported at Q equals 1. Its sign shows which direction the reaction goes to reach equilibrium and tells us the magnitude of KQ. If delta G is negative, forward direction. If delta G is positive, then it's reverse reaction. The relationship between these two, they're deriving a formula here, and I don't really want to mess with it too much, but this one comes from the notes. Board. And they basically go through the steps of deriving it. You've got the steps. I don't want to mess with it. Standard delta G for the reaction equals negative RTLNQ. I'm pretty sure this is the last board and pen left in the whole building. This one's on the AP sheet. So if you need to relate delta G and Q, check your formula sheet. A lot of times, like the example that we're going to see, it wants to know the value of K. And so you have to solve for K. So it's not on there. You can take this formula to find K, but you have to figure out how to do it. So you've got natural log of K equals delta G over negative RT, and how do you get rid of a natural log? Math students, you know how to get rid of a natural log? On your calculator, press the button that says second and then hit natural log.
Oh, just E.
It's E, yeah. So basically you want to do E to the lnk equals E to all of this. And what that gives you is K equals E to the negative delta G over RT. Or the way that it's written on your paper, K equals E negative delta G divided by RT. Same thing. If the idea comes up, this is probably what AP wants you to do right here. So a couple of examples and then we'll be done with this section. Example 2, consider this reaction 2SO2 plus O2 yields 2SO3. Oh, come on. Same reaction we've been working with for a while. We get all of our numbers. Delta H, negative 198. Delta S, these are standards, negative 187. And we have standard delta G, negative 142. All of these are standard states, and it even goes as far as to specify that we're at 25 degrees Celsius, which is 298 Kelvin. First question says, calculate the value of the equilibrium constant at 25 degrees Celsius. At a standard state, what is K? And so the formula that we just derived or didn't derive at the top of the page, E negative G divided by RT. So negative, and here's delta G, negative 142. I'm going to leave the units off for simplicity here. R. There's 3 different values for R on your AP formula sheet. We're working with joules and kilojoules. One of your values for R has joules. Keep it in the family. Use the joules. 8.314, and that's joules. Let's make it kilojoules. And temperature is 298 Kelvin. Quality control time. Looks like everybody's putting their calculator. Might be best if you calculate all of this before you put it as the exponent for E. You get it? Everybody agree? So what'd you get?
I got that.
Oh, you got it. You just were scared by the magnitude of the number. So
Because we've been working with like decimals.
it's possible the equilibrium constants are extremely large. It's also possible extremely small. So if you don't trust yourself, you can calculate it a second time. But if you get the answer both times, you got to trust your calculator. Just write the answer down and move on. We don't have time to diagnose, problems that we think are problems. We've got a lot of work to do on the AP exam. If you get an answer, write it down. You can't double check everything. There's just not enough time. Next question, B. What is the value of KEQ at 100 degrees Celsius, assuming that delta H and delta S don't change? So everything else in here should be the same, right? The only thing that changes is the temperature. Plus.
Oh, 100 Celsius.
Yep.
Kelvin scale is so funny. We should be getting 19 better. It's so much more simple. Fleet margins from Fahrenheit to 19, same as Celsius to Kelvin.
Instead of 273, it's 459. Everybody's answer agree with this one? Okay. So from here to here, we increased the temperature. The value of the equilibrium constant went down, but this is still an incredibly large number. It means this reaction is going to go through pretty fast. Part C, it wants to know at what temperatures will this process be thermodynamically unfavorable at a standard state. Remember how we did these? We started with this formula. And we want it to be thermodynamically unfavorable. Which means that delta G has to be greater than 0. We've already got a lot of these numbers. We're looking for temperature, and the rest of it's just plugging in numbers. Remember, change joules to kilojoules. I get an answer. (1,059 Kelvin. Everybody agree?